Hello everyone and welcome to another video where today I would like to talk about another video that has been recently released by Kryptonite Physics. How exciting, I know. I dropped everything I did and I immediately went on to have a look at this video. Now, the thing about this video is that it is essentially a rehash of a discussion we've already had, but this time I have done a little bit more research specifically into color vision. And I believe I am now able to debunk this point more thoroughly. And I don't like the word debunk. I still use it though. Yeah, let's get into the video. It's just 1 minute and 20 seconds, but it is part of a more large, of a more thorough discussion. So let's have a look. It is about seeing the color of stars, somewhat unsurprisingly.
If you can see the color of stars.
And I'm pleased to say that the audio quality, as well as the narration voice, has significantly improved. Chris, nice to see that your videos are improving.
With the unaided eye. This is a big problem for NASA and astrophysics.
I mean, it really isn't. If it were a big problem, don't you think we would have come by it by now? But regardless, let's continue.
The cone cells in our eyes, responsible for color vision, need a minimum amount of light to see color.
That is correct. What, dear Chris, pray tell, what is this minimum amount of light?
The minimum amount is 0.01 lux.
And that's completely wrong. We'll see I'll go into detail as to why that is. Now, spread over the whole field of human vision, this number would be correct-ish, certainly within the right magnitude. If a light source, if we would get 0.01 lux, and this light would be coming in equally over the whole field of human vision, this number would be in the correct order of magnitude.
Yet the brightest star, Sirius, we see as blue-white. This is its official amount of light in lux getting to Earth. It needs to be over 1,000 times brighter to see its color.
We will talk about all of the details in just a little bit, but that's wrong. And the video was very short, but he gives a formula at the end, which I'm very pleased by. I have had a look into the origin of this formula, and it appears to be roughly correct. I must admit I have never seen this formula before, but I have looked into it and I agree with it. I've since found out that in one of the many textbooks that we used during the bachelor course of my astronomy degree, we had a very, very similar formula which I will be using. It differs only extremely slightly by not having by not dividing it by 2.5 on 2, but by 2.5. They omitted the 1, 2, which I think should be completely fine. So I have no quarrels with this formula. But I do have quarrels with something else. All right, then let's continue. What do I disagree with? What do I have quarrels with in this video? Well, we turn once again to my trusty Iron Notes notebook for Vision Stars, round 2. First of all, Kryptonite Physics claim we can only see color above 0.01 lux. All stars give less light, apart from the sun, of course. So we should not see their color, but we do, and this is some sort of a problem. Before we go into the details, a quick refresher on vision that was covered both in my original series about the Kryptonite Physics vision and stars claim, but also in his video to a satisfactory amount of detail. We have two types of receptors in our eye. We have cones and we have rods. Now, both cones and rods have subtypes, which are not important for this purpose. Cones see color and they're less sensitive, and rods see black and white and are more sensitive. And if it's dark outside, gradually, or dark inside as well, gradually the human vision shifts um, from observing with cones to looking at things with the rods, right? Because the rods are more efficient, more sensitive. The cones function in the following way. We have three types of cones: the S, the M, and the L cones, where the S cones see red, the M cones see green, and the L cones see blue. And the combination of these three in our brain generates color. Now, you may know someone who's colorblind. I have a colleague who's colorblind, and I have a friend who's a little colorblind. And they usually, what happens is that the cones, for example, the red and green cones, are indistinguishable to the brain, and thus most things that are either green or blue or red look a yellowish brown to them, typically. Regardless, in normally functioning human eyes, we have three types of cones, and these cones, the combination of the signals from these three cones is interpreted as a color by the brain. In this case, for example, this would roughly correspond to yellow, right? So, as we've covered in the last series, rods can see almost individual photons, not exactly individual photons, but 5, 6, 7 photons are completely fine, and can be detected by rods, which is remarkable. And cones can see from the hundreds to the thousands of photons. Now, you may wonder, where do I have this from? Well, I asked Kryptonet Physics in the comments of his video for his citation for 0.01 lux, and he linked me to 2 papers. Now, one of these papers, to my understanding, does not say anything about the transmission between the border between scotopic and mesopic vision, from as far as I understood it. But this one here kind of does. This is a review paper about all things color and eyes, which is actually a very helpful paper and a very good resource. Unfortunately, Chris either didn't read it properly or didn't fully understand it. And they say here that mesopic vision, here under the mesopic thing, there's a cone threshold. So 200 and let's say 50 here for practical purposes. 250 photons are sufficient for a cone to go into mesopic vision, so to see some color, which is interesting. We have here 3 cones and rods, so both kind of in they work in unison, if you will. And we need around 250 photons for that. So cones can see 250 photons. So arbitrarily, let's say this. Let's say we multiply this by 100. Mostly because we need multiple cones, of course, to receive a signal, at least 3. But I imagine, and I have no experience with neuroscience whatsoever, but I would imagine that just 3 cones receiving light is a little bit too less. We need more than 3. So I'd say a couple of dozen are fine, right? So let's say 30 to 50 should be fine. This is more or less an arbitrary number, I do agree. However, as we will see later, this is not a bad estimate. So let's say we have 25,000 photons, which are, let's say, for a typical human in conditions around the scotopic, mesopic thing to see color. So 25,000 photons need to hit exclusively cones for us to be able to see color. This is our base assumption. And by the way, these photons are like 1.6 times 10 to the negative 7 lux. So way below 0.01 lux. By the way, 0.01 lux are this many photons. This is the sign for photons, it's a gamma. 1.6 roughly times 10 to the power of 9 photons, which is about 260 gammas or photons per cone. And this is interesting. So below 0.01 lux, if we were to spread all of this out in human vision, if we go below roughly that, not enough photons would hit the cones. But this is the very point. It is not spread between all cones. And this is what this paper here, or typical studies like it, assume, that all of the light is spread equally along the field of human vision. But what about a specific spot? Let's say the binocular vision of the human field of view is around 120 degrees. This is the one that I'm working with, just for visualization purposes, right? And let's say you have, in all of your field of vision, you have an equally lit background. We have then roughly 250 photons per cone, which is just about the detection threshold, which I could be convinced that this is not enough to see color. However, if we have a local point, very local, don't forget the angular size of a star is absolutely tiny and is for all practical purposes a point source. So we have a single point where more photons of a specific wavelength, thus color, reach the eye. These are not spread amongst all cones, because then we wouldn't see the star at a single position. We would see it spread out over the whole field of vision. But this is not how vision works. This is concentrated, this is focused by the human eye to a specific set of cones. If a few cones can see the star, or if the light of the star hits a few cones and it gets more than 250 photons there, locally we can see color, even though over the whole field of vision the light can be well below 0.01 lux. And this is the important point that cryptonophysics Chris here is I think missing, because he gets the idea from this paper that the 0.01 lux applies to being spread out over the whole field of vision, which is not what is happening with stars, obviously not, right? Okay, so I would like to summarize here the claim that 0.01 lux is the limit, or is the beginning of scotopic vision, is in principle not wrong if it is applied to the whole field of vision, which is certainly not the case for stars. Thus, this assumption is just wrong, just incorrect. Okay, so an individual star may be seen by as few as a couple of cones. And in this case, in this very specific case, it is cool as long as we have locally more than 250 photons per cone. Or thereabouts, of course. I imagine this this differs with the quality of the eyes of the observer. So, let's look now at stars. I've looked around. The source there will be linked, I hope, if I remember, in the description of my video. I've looked around in hobby astronomer forums, and there they say that roughly around 2 magnitudes, 2 to 2.5, I found varying opinions on that, magnitude is when most people see no more color with the naked eye from stars. And now I wondered, well, according to his very own formula, which I believe is fine, what lux would that be? Well, so I calculated with this formula, 2 magnitudes of brightness. Magnitudes is a little bit of a stupid unit, because less in terms of number, so 1 magnitude is brighter than 2 magnitude. For some reason, astronomers just do things like that sometimes, which is roughly 3.3 or 3.4 times 10 to the negative 7 lux, which would be 52,000 photons. Now that is interesting, because that is only a factor of 2 away from my admittedly very speculative estimate here. So we are doing fine. This is good. This is only a factor 2 away from my estimate. So I would argue that we should see color of the stars that are roughly that are brighter than 2 magnitudes. Down to 2 magnitudes, we should see the color of the stars. From every material that I have found, this lines up with our estimate, and it lines up with what hobby astronomers see. And this I think should be completely sufficient. So we don't have a problem, Chris. NASA's fine, certainly. The whole field of astrophysics is also fine, certainly. Um, this is just a question about the light being spread out over an area or the light being concentrated into one little point that gives us enough light for us to see color in it, which, as you can see from my estimations, it should. So no problems to be detected here at all. And now we follow this up by a note of methodology for krypton physics, because his point is kind of flawed, I think. His premise is flawed. Even if 0.01 lux was correct, something would have to be off, right? So we have a limit of 0.01 lux. This limit translates to an apparent magnitude of minus 9.2. Now, if you're not an astronomer, this number doesn't mean anything, but to an astronomer, this is ridiculously bright. Venus from Earth has around, I think, minus 5 magnitude, and magnitude is logarithmic. So minus 5 is not half as bright as minus 10, but it's like by several orders of magnitude less bright. So if our detection for color vision was 0.01 lux, regardless of how spread out it would be in the field of vision, we shouldn't see any star's color apart from the sun. But obviously we do. And the thing is, apparent magnitudes are photometric measurements. They're independent of distance. The apparent magnitude does not say how far away this thing is. It is a simple direct measurement of how bright this thing is. So if you say, Chris, that we shouldn't see any of the stars, you're in the same breath saying that all the magnitudes are wrong. So independent of the distance, all stars should be too dim, and the apparent magnitude is directly measured. It has no dependence on distance. It does not care about the distance. Not at all. Now, of course, we know the distance to most of the objects in the night sky nowadays, but this is independent from its apparent magnitude. We don't need the one to calculate the other, typically. Of course, I imagine there are exceptions to that. But typically we don't. So if you say all of the apparent magnitudes are wrong, apologies, I'm still a little sick. If you say all of the apparent magnitudes are wrong, first of all, then why are you using them in the first place if you say, well, it's wrong? If you want to show that the assumptions would be wrong, well, obviously they're not, as shown in the video. We're doing fine. Within our system of reasoning, we are doing okay. So you're not showing that we'd be wrong, first of all. And then why use them if you think that they're wrong? If the conclusion adds up, I don't get it. Maybe I'm not getting something. But the thing that really bothers me, for example, things that are around this brightness, about minus 9 point something magnitude, for example, an iridium flare. I have a picture here. Should everything in the night sky be as bright as an iridium flare? They come from satellites in a very, 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 very specific geometric position. Look how bright this is. This thing. That's not a comet. That's an iridium flare. You can read up on what exactly this is on Wikipedia. I would encourage you to do so. Look at that. Should every star be as bright as that? Because this has minus 9.5 magnitudes. So, Chris, what are you saying? If you want to say that the stars have to be closer, that doesn't change their apparent magnitude. You still wouldn't be able to see them even if they were in your room, as long as they wouldn't be resolved. Apparent magnitude is a measurement that is independent of distance. It is not important how far away these things are. I can't emphasize this point enough. If you think the apparent magnitudes are wrong, I would encourage you to measure them. I don't know what else to say. So please, if you could clear this up for me, Chris, maybe that would be highly appreciated. Also, and I know I need to do some bickering. This is a good etiquette almost. why have you never answered any of the questions from the original video series that I did? Like, I don't recall, in November maybe, or was that December? I genuinely don't recall. Why did you never answer any of these? Why are you silent about having made up citations with AI? That's odd, Chris. That's really odd. But regardless, I hope you enjoyed this video, Chris, and everyone else who's watching. And I think we've set this aside for now. I think we've done a thorough job. Yeah, so with that, I think we are done for this video. If you enjoyed this video, maybe consider leaving a like. If you enjoyed it a lot, maybe considering subscribing. And I hope I will see you in the next video and or live stream, as this is now a possibility that I may do a live stream sometimes, but only if my voice has somewhat recovered from me being sick again. Yeah. So I will see you in whatever form of content I will upload next, I hope. Until then, have a nice time. Goodbye.